All right, folks, welcome back. Here we are finishing up Unit 8 of AP Calculus BC. We've got one more video here on Section 813 where we're going to look through a few more examples regarding finding arc length and calculating the distance traveled by an object in 2 dimensions. So, previously in Calculus AB, we learned how to find the distance traveled in 1 dimension by using an integral of the function that represented the motion in that one direction. Now, with the arc length formula, now we can actually find the distance traveled by some object in 2 dimensions. And that distance traveled is just the arc length. You know, if you imagine this smooth curve, the distance that was traveled by this object from its beginning to its end is just the length of this curve. Okay, and no matter what the curve looks like, that's going to be the case. All right, let's look at example 3. This comes to us from the AP Calculus BC exam from 2012, free response question number 2. It's a calculator section. And this one's going to actually require us to use a slightly different form of our formula than we've developed thus far in this unit, because this actually fits into a topic we're going to talk about a little bit later. So for time greater than or equal to 0, a particle is moving along a curve so that its position at time t is the function x of t, y of t. At time t equals 2, the particle is at position 1, 5. Not that we need to know that for this, but it is known that dx dt equals the square root of t plus 2 over e to the t, and dy dt is equal to sine squared of t. So basically, we had our general arc length formula that was dx quantity squared plus dy quantity squared, the square root of that. And then, depending on what our curves were in terms of, we set it up so that we were multiplying by the appropriate differential. Well, now, in this function, our curves are in terms of t, so we want to multiply by dt out here and divide both of these by dt squared in the radical. And when we do that, that means that we're turning this into the square root of dx dt squared plus dy dt squared, giving us our arc length. And so to find the distance traveled, we're going to take the integral of square root of dx dt quantity squared plus dy dt quantity squared with respect to t. And now, since everything's in terms of t in this arc length formula, we're going to need t as our limits of integration. And so we're going to use time 2 and time 4. And there's our setup to find the distance traveled by the particle. And now I can just go ahead and do that using my handy dandy calculator. I'm going to go ahead and go, let's see, integral of the square root of the quantity square root of t plus 2, close the square root, divided by e to the t, close the quantity, square that quantity, plus the quantity sine of t, quantity squared, that whole quantity squared. I guess I could have just done sine to the 4th of t, and close the radical. Now we're going to integrate that with respect to t from 2 to 4. And hopefully I put all the parentheses in the right place. We'll see when I hit enter here and what it outputs for me. The waiting is the hardest part. Sorry, I won't sing for you. That might be a little too much for everybody. It does take quite some time to get some of these integral values on my calculator. I'm just hoping that it will eventually do it. Wow, this is phenomenal. There we go, finally. We get 0.651 for our distance traveled by the particle, with 0.650 also acceptable. And that's the distance traveled by the particle from time t equals 2 to t equals 4. All right, example 4. comes to us from the 2011 AP Calculus BC exam, Form B, free response question number 4. This is a non-calculator question. So we've got the graph of a differentiable function, y equals f of x, with domain from 0 to 10, as shown in the figure to the right. The arc length of the portion of the graph between x equals 0 and x equals 5 is 11. So that's our arc length here is 11. And the arc length of the portion of the graph of f between x equals 5 and x equals 10 is 18. All right. Now, part D of that question tells us the function h is defined by h of x equals 2f of the quantity x over 2. The derivative of h is h prime, which is equal to f prime of x over 2. And we're asked to find the arc length of the graph of y equals h of x from x equals 0 to x equals 20. So the first thing I'm going to do in order to answer this question is I'm going to set up an integral for the arc length of y equals h of x from x equals 0 to x equals 20. Now, h of x is a function in terms of x, so my limits of integration are in terms of x. This is going to be square root of 1 plus dy dx squared. And since the function is h of x, that means that dy dx is h prime of x. And so this is the arc length that we're trying to find. Now we know that h of x is equal to 2 f of x over 2. So we can turn this equation into something based off the arc length of f. Since we know the arc length of f on the entire interval from 0 to 10. So let's see what happens here if we make this substitution. You know, h of x is equal to 2f of x over 2. So let's replace, let's see, how do I want to replace this? The derivative of h is h prime of x. So h prime of x is going to be replaced by f prime of x over 2 here. Let's see, how do I want to best replace this? So we know that h prime of x is equal to f prime of x over 2. So I can replace this h prime of x with an f prime of x over 2. And then I think the easiest route for me from here is going to be to make a substitution, because we know the arc length of f prime of x is used to determine this arc length. So this is almost the formula for the arc length of f prime. And if we replace this with a t, then we can actually replace this arc length with the values of the arc length from the curve. So I'm going to make a substitution. My substitution is going to be t equals x over 2, in which case dt is equal to 1/2 dx, or dx is equal to 2 dt. Now let's see what happens when I make this substitution. My limits of integration are values of x. So I'm going to change them over to be values in terms of t, based off of this substitution. So when x is 0, t is 0 divided by 2, t would be 0. When x is 20, 20 divided by 2 is 10, so that changes my upper limit of integration to 10. This becomes the square root of 1 plus quantity f prime of t, quantity squared. And then dx is equal to 2 dt, so I can put the 2 out in front here and make this dt. And now the beauty part of this is that this formula right here represents the arc length of the function f from 0 to 10, which we know the arc length from 0 to 5 is 11, the arc length from 5 to 10 is 18, and so I can replace that entire thing with 29 for the total arc length, and therefore the arc length of the graph of y equals h of x from 0 to 20 is 58. All right, one more example here. Example 5, we're going to find the exact length of the curve from x equals -2 to x equals 1 algebraically by using anti-differentiation. So I want to set up my integral formula. We want the integral from -2 to 1 of the square root of 1 plus dy dx quantity squared, since y is a function of x here. So we need to figure out what dy dx is. I take the derivative with respect to x of both sides of this function. And therefore, by the fundamental theorem of calculus part 1, dy dx is equal to the square root of 3x to the fourth minus 1. Because we've got a constant lower limit of integration and just x as our upper limit, so we can substitute that into the integrand, and that gives us dy dx. So this is equal to the integral from -2 to 1, the square root of 1 plus the quantity, square root of 3x to the fourth minus 1, quantity squared. Simplifying my radical here, this becomes 1 plus 3x to the fourth minus 1, which becomes the integral of square root of 3x to the fourth or the integral from -2 to 1 of x squared times the square root of 3. Oh, I'm running myself out of room here. And then the antiderivative of that is going to be x to the third times the square root of 3 over 3, evaluated from -2 to 1. And this is going to be root 3 over 3 minus -8 root 3 over 3, which gives us 9 root 3 over 3, or 3 root 3, as the exact length of this curve using anti-differentiation. All right, that's our last example of this lesson. Go ahead, do some practice with this stuff, and we'll see you next time when we start Unit 9. All right, everybody, have a great rest of your day. See you next time. Bye-bye for now.